you can just put all these things together. And delta P is equal to, where is it? Well, look, forget about that. We know delta P because I just wrote it. This delta goes here, all of that. So we know delta P. We go to Poiseuille. We get to Poiseuille this way. By the way, these details mathematically are in the textbook. Maybe I'll indulge in skipping a few steps. One formula I remember is that delta P, and you should as well, is equal to the friction factor 4 times the flow length, in this case h, over the spacing, meaning the hydraulic diameter, by the way, hydraulic diameter, and then 1/2 over rho u squared. This is the general formula, which comes from a force balance, the balance between the force due to delta P from the bottom and all the taus accumulated or integrated over the side walls. That lesson we experienced earlier in the course. And but we have a fully developed laminar flow, so that means F is a Poiseuille number divided by the Reynolds number based on hydraulic diameter. So that's one substitution. The Reynolds number is U dH divided by mu. The Poiseuille constant for a slit is 24. And finally, this U squared is equal to, well, no, forget about U squared. I am going to forget about that. I simplify through one of these average velocities, and that the single U is m dot 1 divided by rho, and then the cross section, which is d times w. Another substitution to make has to do with the hydraulic diameter that appears twice. I'll make a drawing to invite you to remember the answer to the question of how big is the hydraulic diameter of a slit. And that drawing is the following. So you assume, let's imagine you're looking at the slit. Here's the slit. And here comes the m dot 1. The spacing is d. Let's blow this thing up. So here's d. And the hydraulic diameter is a make-believe diameter of a round pipe that to the stream that flows through the slit. By the way, I'm going to make a drawing that refers to the view from the bottom. Anyway, the flow goes into the blackboard. Okay, here's that flow. If the stream would feel friction against the walls as severely as through a duct of diameter d, then the hydraulic diameter would be this one. But that is not the case. The air that flows into this slit from you into the blackboard is more liberated because it experiences no friction on the top side and bottom side. So the so-called friction effect is less intense. and that is equivalent to a round pipe of larger diameter. And that larger diameter is the hydraulic diameter, which for the slit happens to be twice the spacing. So when you see a slit, you should see a conduit that liberates the flow. If you compare the slit of spacing D with a pipe, round pipe of diameter D. Hydraulic diameter of the slit is twice as big. So these two things, meaning dH to power 2, are the same as 4D squared. So these are the substitutions you make. And you arrive at the formula. Here's where I skip. The formula for m dot 1. This is an intermediate conclusion. M dot 1 equals d cubed w 12 nu h, and then g b delta t h from the pressure drop contribution. The height drops out. We are in fact reporting to the user the mass flow rate m dot 1 per unit of length in the third dimension, which does not count. And it is this that you substitute into the formula for the total heat transfer rate. And that conclusion I'll list here at the bottom turns out to be, because you see when you multiply by n, you'd end up dividing by d. So the formula for the total heat transfer rate in the small d limit is 1 over 12 nu. And then rho Cp, okay, W again. And then L G beta delta T squared, and then D squared. I better clean things up. And okay, the competitor to this regime of narrow spacings is the other extreme called wide spacings. Here's the box again. And wide spacings means that there are only a few plates in the picture. We still have H, L. This spacing is D. There is chimney flow, of course, but the spacings are wide enough. What does wide enough mean? Wide enough means that the spacing is bigger, sufficiently wide, so that one plate is unaware of its neighbor, which means that the boundary layer that rises along one of them is skinnier than capital D. So the large D limit means that D is greater than the boundary layer thickness in natural convection. This is a lesson you were given in heat transfer. If you did not have heat transfer, that's not a problem. The formula is in the textbook. The boundary layer thickness scale, here we're doing a order of magnitude analysis because that's easier, is of the order of, in fact, I'll put it this way, divided by the length scale h is the Rayleigh number based on h and delta t obviously between this T0 and, sorry, between T max and T0, raised to the power minus 1/4. The Rayleigh number has a formula. Sorry, Rayleigh number is shorthand. It's a dimensionless number. Namely, G beta delta T, H cubed, divided by alpha nu. You know what? Write it down because it's good for the soul. So it's also good for hand to mind coordination. This is, of course, mu divided by rho. Alpha is air thermal conductivity divided by rho Cp. And now something you may have not heard before, or maybe you heard it incorrectly. I would say all heat transfer manuals, I wouldn't call them books, claim that this dimensionless group in natural convection is the ratio of the buoyancy force, because you see delta T and beta on top with G, the gravity, buoyancy force divided by the friction force. This mu here means friction. Yeah. There are only two forces in this so-called control volume. Two forces. One is this delta P from the bottom that depends on, it's basically due to buoyancy, the difference in the density of air column, and friction against the walls, also known as Poisson flow. That's the friction. So only two forces. And the Rayleigh number, everywhere you look in every calculation, is enormous. In this room is probably 10 to the power 10. Meaning the Rayleigh number referring to boundary layer flow, in our case descending along this wall because the wall is cold, see, and the room air is warm. So if this were the ratio of buoyancy friction divided by friction, air friction, it means that this boundary layer is accelerating very, very fast and getting out of control, getting into not existing anymore. But the flow is steady state, you see. And that is the trick. There's a perfect balance between buoyancy and friction. And the name for that is steady state or stasis, which is nature. This dimensionless number is not a ratio of friction divided by, buoyancy divided by friction, the ratio between two forces. It is simply a dimensionless temperature difference. Obviously, because if delta T is small, then the Rayleigh number is small. And if the delta T is 0, Rayleigh number is 0, and there is no boundary layer, no flow. Simple as that. Okay. What we do next is the following. We look at the distribution of temperature away from one wall. So this is the wall. And this is, well, you can think of this as the other plate. The air in the gap away from the walls is of temperature T0, meaning the temperature in the air that's not touching the walls is T0. And then closer to the walls, the air becomes warmer. And this is the boundary layer region of length scale delta. Delta natural convection. That's the distribution. It is important, the drawing is important, because it shows you a temperature gradient at the wall. Here's the gradient. The gradient, in other words, it's like in skiing. You have a slope, there is flow down the slope. You and your skis are actually going in one direction, which is downhill. So this slope drives the heat current Q1. Q1, which is the object of the game here. How does the heat transfer rate depend on delta T? Q1 is equal to the, meaning the heat transfer rate from one wall, not equal, but I say of the order of magnitude, of the wall surface, which is HW. This is from Fourier. And then the conductivity of air, and then the temperature difference divided by the distance, which is called the delta natural convection. I'll stop writing this natural convection because most of you would think I'm talking about North Carolina here. Okay? North Carolina is a lot more important than the mistakes you find in a handbook. All right, so that's the answer to this Q1. You multiply Q1 by the number of plates, so the total heat transfer rate from the entire box is equal to N times Q1, and from this formula you import Q1 and arrive at a second expression, which in an order of magnitude sense reads as follows: L over D and then HW delta T K over H, and then Rayleigh number to power 1/4. If you want to practice your, algebraic dexterity, do that at home. We have two expressions. Two because there are two extremes. This one very soon will be Roman 1. This other one, Roman 2. You see here, Roman 1 is essentially total heat transfer rate divided by W. meaning per unit length perpendicular to the blackboard, is the same here. And here's the drawing. I'm going to make a drawing that does not confuse you, so I'll use this same frame for Q, obviously divided by the third dimension, 0, 0, and here's let's say, the spacing D. Roman 1. The heat transfer rate would increase as a parabola as D increases. Hey, but wait a minute. This is the wrong direction to think, because Roman 1 is true in the small d limit. In other words, don't draw conclusions that do not refer to reality. This is what you discovered. Nothing else. You discover the small d end of this parabola. Meaning, if you only know Roman 1, and you want to have high heat transfer rate density in this package, because packaging means putting more and more stuff in a box, then to go in that direction is the direction of cheering that you discovered fool's gold. This is not for you. Meaning that you pendulate in the opposite direction. Maybe you'll find gold in this other direction, which is called large D. And large D gives you a equilateral hyperbola that you've seen before, which tries to fool you the other way. It tells you that the way to large heat transfer density is toward small spacings. This hyperbola is true in this other limit, and nothing more. And that is why the actual curve of heat transfer rate versus the single degree of freedom is something that fits under this tent, namely this curve. And some people have spent PhD thesis long efforts to find this curve, the one shown in pink, Q versus D. But finding the curve is really not the object of the game. Finding the spacing where the, let's say, diversity of Q box max is located. And that nirvana is available at the intersection of the asymptotes. And so if you equate these two boxes, you arrive at the punchline, which is that, so if you set Q Roman 1 the same as Q Roman 2, you arrive at the spacing, which is H Rayleigh number based on H to minus 1/4, which, not surprisingly, is the same as the boundary layer thickness scale. So this is the design secret, and it is a secret because it's frankly, maybe it's not a secret anymore after my efforts to teach it. because if you know the fact that the package should be a package not of hot plates, but a package of boundary layers, the only thing you have to remember is the ability to predict the boundary layer thickness. And then in the package, you pack boundary layers the way that you pack crayons in a crayons box. Simple as that. Everything else is for those who do not take your course in design in nature. By the way, this is what the bees do to create their channels. Their channels are round cross-section versions of these slits that I've been sketching on the blackboard today. We will continue.